Okay, so we start in 1 minute, please. Find your seats.
Yes, online.
Yeah. Can we get the confirmation from the online participants that you can hear us? Maybe a confirmation in the chat. Thank you, Christina. Very good. Okay. And welcome to this first science session of the GHRSST meeting. I'm Steinar Istud, sharing this session, and with me I have Pia Englist, who's the rapporteur. First, we would just like to ask to thanks the first speaker here for a brilliant poster session and icebreaker yesterday. And we'll now kick off the first science session of the GHRSST meeting. It's about advances and challenges of surface temperatures in the polar regions. So we are now in the Nordic countries and we are close to the polar region, so there will be a natural polar focus in this year's GHRSST meeting. So over to Jakob and the keynote speaker of today.
Thank you, Steinar. And yes, I think it was very interesting yesterday, poster session, and I hope, and also the talks. So I hope today will be just as interesting and maybe even more with the science sessions and going into some more science topics. To kick off, let's see, yeah, I have here a presentation I call the Advanced Polar Surface Temperature and Sea Ice Monitoring. And essentially it's an overview of, or it's a selected overview of some of the research and development activities that that is going on and has taken place in the unit that I'm leading at DMI called Satellites and the Arctic. It's in the National Center for Climate Research. So that also means that there are a lot of contributors to this presentations, and I have tried to credit all of them as I go through the presentation, and I hope it worked. But it really it's a sort of a snapshot and a selected some selected topics that I thought would fit in here. So. Well, first, of course, the motivation. Why are we looking at the polar regions? Why are the polar regions interesting? If we start with the Arctic, well, I think you probably all know the issue here. Climate change is most pronounced in the Arctic. It's represented by these very famous OSISAF sea ice extent graphs and the trends, where the one to the left here is the Arctic sea ice extent, and you can see the very pronounced decline both in summer and wintertime sea ice extent. And that with that sea ice extent, that a lot of associated feedbacks and associated changes occur, like diminishing snow cover, sea ice, land ice, and permafrost. And it's really transforming the Arctic and has far-reaching consequences. And it's been predicted in future scenarios that actually we will have ice-free summer in the Arctic by the 2050. Sorry. So that's a well-known story. A lot of changes have happened since the early 80s. But what's also then turning to the south in an Arctic and the Arctic sea ice extent, it has been relatively stable for many years. That's the middle figure here. But in the recent years, might be a tendency actually that we also see some kind of rapid or at least pronounced decrease in the Antarctic sea ice. And to the figure to the very right is is the Antarctic sea ice extent as a function of months, where you can see the recent years, 23, 25, and also 22, have shown a really significant and record low sea ice minima in the seas around Antarctic. So maybe there's the Arctic is a precursor, the first mover in that respect, and Antarctic is coming in respect to sea ice loss. So a lot of things is going on. So it's important to monitor the polar regions and do it accurately. But there are also quite a few challenges when you do that. And that's what I'm trying to cover, some of these in this talk at least. So I'll talk about the challenges for observing the sea surface temperature in the high latitudes. Then I'll go into the sea ice surface temperature because it is really dynamic regions, the polar regions, where you have a mix of open ocean, marginal ice zone, and sea ice. And then, so I'll talk about the challenges for sea ice surface temperature. Then I'll talk about the challenges the challenges with this sea ice concentration and SST and IST consistency in these regions, and then something about assessing how can we in new ways assess the climate change in the polar regions using these products and the things and the new developments that we are seeing. And finally, conclusion and way forward. So this is really just a snapshot of the issues, an example from our own backyard, I would say, from our own production. Many other examples have shown similar results. Just indicating here on the top figure to the left is really the validation for a climate data record for the SST CCI version 3. The AVHRR validated as a function of latitude, and as you can see, well, first of all, it's a really a nice data set. I think it's probably the best, one of the most accurate data set that exists. But nevertheless, you can also see that at least for I don't know how obvious it is or how clear it is, but the top figure is the top graph is the mean difference. And the bottom line on the top panel is the standard deviation. So you can see that approaching the northern latitudes and in the Arctic, we really see some distinct differences and higher uncertainties, standard deviations, and a negative bias. And that's the level 3 product. It's taken as a level 3 in the DMI system as in the production of the global SST IST that I'll come back to later. So that means that we have, just to illustrate that we do still have issues on the SST product accuracy in the high latitudes, and especially in the Arctic. In the southern hemisphere, it looks more stable for the level 3. And the lower panel is just from this C3S global SST level 4 DMI analysis, and also for the SST level 4 analysis, indicating that they've essentially, when you do a gap-free interpolated product based on these observations, this is also it resembles very much the sort of the input data. So there is. So there is an issue. It's not both in level 3 and level 4 with higher uncertainties, and that has been documented by, I think, several of you in this audience here as well. That the data and the level 4 products in particular are also show higher uncertainties in the high latitudes and especially in the Arctic. So that's of course also connected with the infrared coverage, the very persistent cloud cover in the Arctic, shown up to the top right figure here, showing that we have persistent cloud cover and limited data return in the infrared. So what to do about that? I won't go in much detail on the SST retrievals today, but just say that what we have done and what we have been looking into is the microwave data records. Are they really the solution to some of this? And the answer is partially a yes. Pia, sitting over here, has made a nice publication on how to include the microwave sea-surface temperatures in the level 4 production. And the panel here shows the improvement that led to, and where you can see that maybe I don't know how evident it is, but you can at least on my screen it's evident that you can see a larger improvement in the performance towards the higher latitudes by including microwave data. It was also evident from the study that you have to including or blending, mixing microwave and infrared. You have to reference one product against each other, against each other in some way, because they have sort of distinct differences and distinct biases that could lead to some artifacts if you don't do that. And I think Mattia Sabatini has also a presentation on this for coastal regions. So including the microwave observations really improves, at least on the level 4 products in the high latitudes, and even making referencing the infrared to the microwave gives actually that was the best result that we could get. On the other hand, for consistency, and there might be other sort of arguments for doing it the other way around, adjusting the microwave to the infrared, because it's a longer climate data record, whereas the microwave starts in 2002, and the infrared goes back to 82. But the message is that it can give improvements. There are also some limitations due to observations close to land and sea ice that of course restricts the number of microwave data, but at least it's not the cloud cover, because they can see through non-precipitating clouds, so observe through that in those conditions. So that's encouraging, and of course with the new the launch of AMSAT3 and with CIMR also coming, I think this is something to really take advantage of in the future. So a few slides about the sea ice surface temperatures and some of the challenges that we are facing there. First of all, it's relatively new compared to the established SST community and the SST science. And so we are mostly also in the high latitude task team. There's been talks about what is sea ice surface temperature actually, how to define it, and maybe having some reference figure similar to the very famous GHRSST SST figure that was made many years ago. But it's really helpful in order to talk about SSTs and different ways of skin, subskin, foundation, and so on for users. And we have tried in a similar way to see if I made the first steps in order to have derive such a figure for sea ice surface temperature. So I'll talk about that, and then something about collection of reference observations is important in the Arctic to validate and improve on the retrievals and the cloud masking. Then I'll talk about the retrievals and consistency. And about inconsistency for different infrared IST products. And in the end, I'll also touch upon the microwave IST. So this is, this might be a bit busy figure. I apologize for that. It is really, as I said, the first take of creating a reference figure, or a figure that can be used to understand the conditions and talk about the conditions for the sea ice. It is it's created by Hoyeon from DI, but it's really an extract of the thermistor observations from a thermistor chain, which has been, as you can see on the right here, it's been drilled into sea ice and measure and put all the way through into the ocean, and then it measures the temperature in the ocean, in the sea ice, and then the snow, and then the surface air with a resolution of I think it's 2 centimeters along this thermistor string. So at this and these two middle panels here, we have just extracted the mean conditions throughout the year for that thermistor chain and for selected buoys, where you can see the locations to the very left. But as you can see, that indicates, well, first of all, the ocean temperature at the ice-ocean interface is relatively stable, and that's also, of course, what we would expect. It differs a little bit in the location due to the sea ice growth and shrinkage and in the thickness. But essentially, it's very stable. And then we have the temperature profile throughout the year that changes. The left panel is from October to June, so it's really I would say, freezing and start of the melting season. Whereas the right panel is from August to October, so that's really from the melting season and then into the refreezing again on the multi-year ice surface, multi-year ice sea ice flow. So you can see that these conditions really show that the arrow bars on the observation shows the variability, which is also in the table below. So in general, the conditions changes a lot throughout the year. It's always, almost always the case that the snow sea ice interface is warmer than the sea ice surface due to the heat flux from the ocean below and through the sea ice. And the temperature profile in the sea ice differs a little bit according to the seasons, as you see. So, but we always have a temperature gradient between the sea snow and sea ice interface and the snow surface, snow skin surface. That's important to note. And that difference depends on the actual thickness of the snow layer. And as you can see on the right, the yellow line on the right shows, for instance, a condition where we have more than 25 centimeters of snow, and that gives a mean difference between the two observations of more than, I think, 15 degrees Celsius throughout that month of October. So there are some differences, and also the variability is of course larger for the snow surface than the snow and sea ice interface. So why is this important? Well, it's important because looking at observations and trying to validate your observations in the Arctic, then most of the observations comes from the equivalent of our drifting buoys in the sea surface temperature world, where there are put out these ISVP buoys on the sea ice to measure pressure and temperature. But once these buoys are put out, they only measure one position, and once these buoys are covered in snow, it gives you a completely different thing than the snow skin surface, which we measure from the infrared satellites. So we have to really think about carefully on how to collect reference observations in the Arctic, and that's something that some activities that DMI has been carrying out for quite some time. In Qaanaaq, it's in the northwestern Greenland, where we have a station there. A field station where we have put out instruments since 2011. And this is just an example of 2 days of a time series where we measure both 1 meter, 2 meter temperatures, the infrared skin surface temperatures, and then the thermal interface of the snow and sea ice, and sort of all the different parameters in the snow sea ice system. So that's important reference data that we are collecting. But we also need to look at some other ways of getting cheap and easily deployed reference data, and that's obtained in this project called Trusted, which is a Copernicus-funded project from EUMETSAT that GORM is participating in. Where we are helping out in designing and developing a sea ice reference buoy that can measure the temperature from the snow sea ice interface and up into the air. And as you can see on the figure here to the left, this is just an example of the first sort of prototype deployment that we did this winter. and we'll now we'll examine those data, and we are giving feedback on the design and on the performance of that instrument, and that will lead to hopefully a deployment of the first batch of these trusted ice buoys. Because it is really important that we have good reference data, because this is in order to determine to improve the retrievals, to look at the errors characteristics of the satellite data, and also improve on the cloud screening. And this is illustrated by well, it's not illustrated, but the inconsistency between the different satellite products is illustrated in this figure here, which is a paper that we have in preparation, and I think there is also a poster on that, where we look at 5 different products of satellite infrared ice surface temperatures. It's covering from Moody's Aquaterra and SLSTR A and B. And these 4 products are from the LST CCI project. And then we compare also against our own DMI and the METNO developed ASTI climate data record. And these are just examples referencing the different satellite products against each other throughout the 2 years. And as you can see, we have large differences. There is a tendency that the LST CCI products are more alike, whereas the ASTI comparing the LST CCI against the ASTI data, that's in the bottom 4 panels here, shows larger seasonal variations. And that's of course interesting to explore in details and to figure out the reason for this. But actually, and these are large differences. If you can see, it's several degrees differences between the different satellite products. But it's actually not that easy to quantify where if the ASTI product is behaving has a seasonal pattern in the performance, or if it's the LST CCI products that have this seasonal performance. So just to tell you that even with these large variations and the comparison against trying to look and validate against the existing IST observation is actually not really easy to figure out. But we're working on that and collecting data and looking into more in-situ data is hopefully the key to figure out and reference these, validate these data, because they have to, as you can see, there were these large inconsistency between the products. They really have to be referenced also against each other, and there must be some. I mean, the reasons for these differences are really interesting to figure out. Yes. Okay, then. So there is some work to do on the IST retrievals for sure. At some parts where when more and more products are coming out for infrared satellite IST. And that's something that we're also working on at DMI, where Zoe and Gorm are working on looking into improving the classical IST retrievals, and not just improving the retrievals, but also trying to understand and the causes for the outliers, for the bad retrievals, and try to model the error characteristics of the ice surface temperature, and to identify the bad retrievals, which can be due to cloud contamination or other issues. We know it's cloud screening in the Arctic is a challenging business. Similar to for SST, we could also look into for infrared SST, we could also look into the microwave. And this is what we have done here. One serious challenge, though, is that the microwave IST signal, the sort of the emission depth, or where this signal comes from, is really the snow and sea ice interface. And as you remember, I hope you remember from the sort of reference figure before, there is a distinct difference between the snow surface temperature and the sea and the sea ice and snow interface. So that creates a challenge. But again, it's a relatively well covered region. It's well covered with the microwave observations, again seeing through clouds, but then providing a little bit different sort of variable than the snow ice surface temperatures. But it's something we're working on. I mean, there's, on the other hand, it's a different information, but there is also some additional information in the microwave, because then that has the difference tends to mimic will be closely connected, as I also mentioned earlier, with the snow thickness. So once, if we can figure out in some smart way and have a reliable snow thickness, then we might be able also to reference and include and combine infrared IST with microwave IST. And that's something, well, we're working on right now. We're working on the IST retrievals in various projects, ranging from the CIMR L2 pad, developing an IST product for CIMR. But we also have the plans to include in the next OSISAF project phase to include and to set up an AMSA near real-time SST IST product. And of course, it's I would say much more tricky than the infrared due to yes, thank you. It's much more tricky in the infrared due to this difference and the ocean and sea ice. I'll hurry up then. Okay, I will. So now we have SST IST, and then the combination of SST and IST is really where there's a lot of potential because of the seasonal changes in the sea ice cover. So we have been looking into the sea ice concentration and IST consistency. And first, the SIC sea ice concentration consistency. There is quite a lot of work done, and I think it's mostly IDA, but also others in the group that are looking into different sea ice concentration products. And as you can see, the three products to the left, the OC458, the SICK high resolution, and the OC450 are all passive microwave-based sea ice products. And you can see they differ quite a lot. Whereas to the left is, for now, we can call it a reference sea ice product. It's a high resolution sea ice concentration product based on SAR that also is developed by DMI using machine learning AI techniques. So anyway, we have some inconsistency in the sea ice products, looking at different sea ice products. And that's also evident from this figure here, where it's a heat map showing the SST on the x-axis and the sea ice concentration on the y-axis. And then as you can see there, we have a lot of, we have some similarities, but also for warm surface temperatures, we have some discrepancies between the different sea ice products. We want to use the sea ice concentration into our SST IST products and get the best sea ice mask that we can get. And so we have created some filtering that really tends to align and tends to improve the consistency between the sea ice products. That's the bottom three panels that shows the filtered data here. It's IDA's work. There is a poster on that. And we have also compared the sea ice concentration product against Landsat 8 sea ice concentration product developed by SNU, the Seoul National University, and in collaboration with them, we have used their product to validate the different sea ice product, and it shows improvement when we do the combined multi-sensor sea ice concentration product. Okay, so now we have some consistent sea ice product. We have SST IST, and then we combine it all into a combined level 4 SST IST analysis. And I won't talk about that, the creation of that today. Pia will go in more detail with that. I'll just talk about what can we then do and what are we working on in order to derive the different and monitoring the polar conditions. We're working on extending the sea ice surface temperature to 2 meter temperature over sea ice. That's some work that was done in a few years ago in Eustace. It's a Horizon Europe project. But we're now improving that using machine learning AI methods. And the figure to the left shows the improvement, which are in particular during the summertime. And it's something we'll work on in this ESA project called Motokusuma that Chris and his group is also involved in. Then we can use the product to evaluate climate models and Era 5 analysis. And this is just an example showing that actually we, in the last IPCC AR6 report, it was stated that the CIMR6 models, climate models, were too cold in the Arctic. And using our data, we actually discovered that that's not the case. It's because they use the Era 5 as a benchmark, which is too warm, which is seen in the panel here. And we can also look at indicators. You're looking at Alex has a poster where he's looking into the over ice marine heat waves and also cold spells. And this is the frequency, the timeline of the frequency of both cold spells and heat waves over the sea ice. And as you can see, we have a distinct decline in the cold spells and an increase in the marine heat wave, having this consistent products. And I think lastly, we just have this. Also have this indicator where we look at sea ice concentration and IST over IST, and as the years go by, and as you can see, we have some interesting information in this product where you can see the progress as we go throughout the year and throughout the years. And the recent years, we're really having some distinct changes. Conclusions. I think that's. So conclusions, there is still room for improvement for the Arctic SST retrievals. There is a role of microwave SST that can improve at least level 4 products, but there are also some limitations in the data coverage. And there is need for reference the different IFC observations and to understand better the uncertainty components in the products. There is a need for a multi-sensor sea ice concentration product because that gives improved sea ice mask, and that's very important when you try to combine SST and IST and the marginal ice zone. And then lastly, there is a large potential for these products that cover both the SST and the IST and give a consistent and improved view on the polar changes in the climate. Yeah, thank you.
So thank you, Jakob, and good luck with all the challenges. The questions will be taken after the 3 first talks before the coffee break. So we go straight to the next speaker, which is Chenlie Shi from DMI. We'll be talking to us about sea ice surface temperatures from C-band passive microwave observations.
So fancy microphone. Good morning, everyone. I'm Høyer Shi from Danish Meteorological Institute, and but where's my slide? All right. And today I'm gonna talk about sea ice surface temperature from C-band passive microwave observation. And my colleague Suman contributed to this work, and I should also mention that Emmy and Ida and Pia and Jakob also contributing to this project together. And yeah, and as Jakob already explained a few minutes ago, there is 2 different kinds of sea ice surface temperature in sea ice system. The first thing is the snow surface temperature, and the second thing is the ice surface temperature, the real ice surface temperature. And if we use infrared observation, we can get the air snow surface temperature, and but the satellite observation of infrared ice surface temperature is quite accurate, but it is always blocked by cloud cover, and so it has not good spatial coverage. But on the other hand, the passive microwave ice surface temperature represents the snow ice interface temperature, and that's less accurate, but it enables more frequent and complete monitoring of ice surface temperature field. And so we're expecting a new satellite in few years. So yeah, and it's called Copernicus Imaging Microwave Radiometer, and CIMR is called as like CIMR, and CIMR is being developed by ESA for launch in late 2020s, and CIMR will improve measuring sea ice and polar ocean at higher spatial resolution and accuracy. And as you can see on the left bottom figure, the CIMR has the much more smaller footprint compared to the AMSR or SSMIS, which is previous passive microwave imagers. And there is a ESA-funded project called CIMR Level 2 PAT. That project is to prepare polar oceans and global land Level 2 algorithm for CIMR. And if all the software, data, algorithm documentations will be available to the public for free of use. So if you want to learn more about this project, you can scan this QR code and go to the GitHub page, and you can find everything. It will be open in a few months, I guess. And I will briefly introduce how we can actually retrieve ice surface temperature from C-band observation. And there are three key assumptions for baseline algorithm. The baseline algorithm is introduced by Lee and Son 2015. And the first assumption is that snow ice interface is an effective emitting layer for C-band. And if you see the plot in the left hand side bottom, and the x-axis is brightness temperature of C-band observation, and y-axis is the emitting layer temperature for C-band. You can see it is very highly correlated, and there's almost one-to-one relationship. So that's the theoretical basis of retrieving IST from microwave C-band. And the second assumption is that the atmosphere and snow layer on sea ice are almost transparent as C-band. If you look at the second figure, it shows the extinction coefficient of atmosphere, and if the very left part is the 6.9 gigahertz, which is C-band, you can see the extinction coefficient or the transparency of atmosphere is very high in the Arctic condition. And also the scattering effect is also very minimal. I will not go into detail about the right-hand figure, but it tells us that you can neglect the scattering effect in C-band for atmosphere. And the last assumption is that the sea ice surface is specular at C-band, which that means the sea ice surface is very smooth for the lower frequency, and its reflectivity can be described by Fresnel equation. And I guess most of you know about Fresnel equation, but in short, it describes the reflectance of specular surface, and the equations are given in the right-hand side. And what we need to calculate reflectivity using this equation is the incident angle and the refractive index of ice. So that's why the reflectance is becomes a function of n refractive index and theta, the incident angle. And my previous colleagues Song and Lee developed a combined Fresnel equation, which is the combination of those two equations, and you can remove theta dependency from that. So the relationship between vertically polarized reflectance and the horizontally polarized reflectance are just a function of it removed the refractivity. Sorry. And so it's only a function of incident angle. And we know the incident angle for our observation, so it is possible to relate those two quantities. And another key part is the emissivity plus reflectance is equals to 1. So that describes the energy conservation. And here is a radiative transfer equation that is used for the retrieval. And the left-hand side, there's a T-P theta, that's the brightness temperature that will be measured by satellite at incident angle theta and polarization P. And the T-up is the upwelling brightness temperature from atmosphere. And the second term, epsilon Ts tau, is a surface signal that emitted from eye surface. And the third term is something related to the surface reflected, the downwelling atmospheric radiation. So what we want to know is Ts here. So this is the most trickiest slide. So you will be free in 1 minute. So yeah, if we rearrange this equation, we can have you don't see my mouse cursor, so we can write the emissivity and in these two equations. If we make a ratio of those two equations, we can remove the denominators, and what we only need to know is the RH, and we can find RH by comparing the theoretical curve and observation, and we can find intersection and find RH, and we put RH again to this equation, and we can find a solution for TS. If you want to know more about this, you can just approach me and ask details about it. So this is the demonstration. So we used input data came from AMSR 2 6.9 gigahertz observation, and we also use ERA 5 atmospheric profiles, and we put those atmospheric profiles into ArcGTOF13, which is developed by the UMaset, the NWP staff, to get the T up and T down and tau. And so you can see the retrieved sea ice surface temperature on the right bottom corner, and all the 5 panels are the input data used for retrieval. And so it is also very important to quantify the uncertainty and the accuracy of the product. And we have a validation plan by comparing the retrieval with the buoy measured temperatures. So as Jakob already showed you, there is a thermistor string observation over the Arctic, and we can extract the snow ice interface temperature from that observation. And it is very straightforward to make a comparison between them. So now we are creating a matchup data set between AMSR 2 and buoy and ERA 5 atmospheric profiles, and it will be available in a few months, I guess. And we have some future research and development plans. And the first thing is the bias correction method. And we expect there must be some systematic bias in our retrieval, and not only C-band, but there's also the higher frequency informations, and that will deliver us some snow condition or temperature, or some more information about that. We believe that those information can be used to correct systematic bias that we expect from it. And before CIMR becomes operational, AMSR 2 will be used for the development, and the developed correction method will be updated with CIMR observation afterward. And here's some application examples, and I got some questions about why do we care about ice surface temperature, and I think these slides can provide some answers to you. And first of all, there is this sea ice surface temperature can be used to estimate sea ice emissivity for several frequencies, and if we can get some emissivity, it can be used to differentiate different kinds of sea ice types. You can see the left. and Li et al. 2017 paper. And also it can be used to estimate sea ice thickness and snow depths as it gives you some information about snow depths. And also the modelers also require some information, temperature information to constrain their model. So on the right, you can see the warm bias in the sea ice model has significantly improved when the both infrared infrared IST and microwave IST was treated to the ice model. And the one last thing is that maybe we can use microwave IST to supplement the infrared IST, because you already saw that there's cloud everywhere, so there's many gaps. So we think that the passive microwave IST could be a good predictor for filling those gaps. And thank you for your attention. And yeah, any questions? Please welcome.
Thank you, Hoyeon, for a very interesting talk and giving us the basis for IST from passive microwave. We await the questions to the question session after the next talk. So we then go to Chenlie Shi from Northwest University. We'll give an online presentation on the discrepancies in different in-situ temperature measurements in polar snow ice surface and the influence on validation of remote sensing ice surface temperatures.
Hello, can you hear me?
Yes, we can.
Can you hear my screen?
That's your screen.
Yeah, okay.
If you go to presentation mode.
Yeah, okay. Hello, everyone. My name is Chenlie Shi. Okay?
Thank you.
I'm beginning. My name is Chenlie Shi. I'm currently a PhD candidate from Northwest University in China. My research focuses on the remote sensing retrieval and validations of ice surface temperature in polar regions, with particular attention to the uncertainties involved in the validation process. I'm very pleased to participate in GHRSST26, and this is also my first time attending this conference. Today I'm going to present my work entitled Discrepancies in different in-situ temperature measurements of the polar snow or ice surface and their influence on validation of remote sensing activity. Firstly, I will introduce the motivation of study. As we know, ice surface temperature obtained from remote sensing plays an important role in polar climate change research. For example, it can be also to quantify the magnitude of the warming in polar regions and to monitor the extent of the ice sheet melting and to identify the leaks in polar sea ice and to evaluate and improve the model data. It must be understood the remote sensing RT is the radiation attenuated by the atmosphere, and then it will be converted to surface temperature using a specific method, like a simulated window algorithm. Therefore, it is necessary to validate the retrieved ST to ensure their accuracy and assess their uncertainty. Here we list the validation results of the remote sensing RT in the past, and the three types of in-situ temperature measurements have commonly been used, include air temperature, long-wave radiation-based RT, like CIMR4 and PIR, and the infrared radiation-based RT, like SI111. In early study, air temperature was frequently used for validation, often resulting in a coded bias in the validation results. The bias was initially attributed to errors in cloud detection by the satellite. However, even after cloud contaminated data was removed, the code bias remained. Subsequently, studies show that when both air temperature and the infrared radiation-based temperature was used for validation. The code bias was significantly reduced or near eliminated. This find suggests that the code bias was large due to the temperature evasion over polar ranges, where the air temperature is often higher than the surface temperature. In addition, since remote-sensing RT presented a direct radiation temperature, land surface temperature product validation best practice protocol recommend use radiation-based measurement rather than air temperature for validation of the land surface temperature. Also, we found even when use the long-wave or infrared radiation-based validation method, previous study have rarely achieved the desired accuracy of within 1 Kelvin. In this slide, we summarize the difficulty in the validation of remote sensing RT. The first is the difficulty to distinguish the cloud and snow. The second is the In-situ ST derived from the radiation-based measurements that are highly influenced by local environment condition. Like in the picture, the rim is often exists in the radiometers, and the near surface atmospheric process like ballooning snow and the damaged dust, which affects the calculation results of In-situ ST, and the future lead to a validation accuracy. Furthermore, as previously mentioned, discrepancy exists between long-wave radiation-based RT and those obtained from infrared radiations. If remote sensing RT was validated by the inaccuracy in-situ ST, it's difficult to determine whether the validation errors stem from uncertainties in remote sensing retrieval itself or from errors in the in-situ S data. Therefore, this research aims to answer two questions. The first is how large are the temperature difference among the different in-situ measurements at the same site, and how much do they affect the validation of the remote sensing RT? Another is what is the optimal approach for validation remote sensing RT product in polar regions. The data obtained from Mosaic application for 1 year was used, including the long-wave radiation-based RT, infrared radiation-based RT, and air temperature. In addition, ground-based cloud remote sensing was also used to identify the clear sky or cloud. And please note that all instruments were carefully calibrated before the start of the Mosaic applications. Due to the radiation-based temperature is derived by converting the radiation values into surface temperature using specific equations. These equations will affect the calculation accuracy of the in-situ ST. Therefore, the radiation-based temperature was recalculated in our study. We didn't provide a detailed derive of the formula, but I think the two key points need to be emphasized when deriving in-situ ST from the infrared-based temp measurements. Firstly, due to the high surface emissivity and the low atmospheric emission within the 8 to 14 macro atmospheric model, the potting of the downward radiation reflected by the surface is negligible. Secondly, for many previous studies, infrared radiation-based temperature was often calculators use the effective wavelength method. See the equation 10 with red font. This approach is generally suitable for satellite sensor with narrow spectral band. However, for the SI111 infrared radiometer, it will introduce significant errors. Therefore, in this study, we adopt a lookup table-based method. See equation 12 with blue font. Similar, we provided the calculation formula for long-wave radiation-based temperature. During the Mosaic application, both upward and downward of long-wave radiation was not affected by rim accumulation. Therefore, the key factor influenced the calculation accuracy of long-wave radiation-based temperature is the snow emissivity. Typically, the emissivity of snow in the long wave bed is set to 0.985. However, notice that emissivity in long wave bed is a function of both angle and wavelength. And to date, there is no measured emissivity spectra available beyond 15 micron. In addition, atmospheric radiation between the radiator and the surface can also significantly affect the calculation accuracy of the long wave risk-based temperature, which will be explained later. The last slide shows presents a comparison of three types of temperature management. As shown in the picture A, air temperature is generally higher than the long wave radiation-based temperature, which in turn is higher than the infrared radiation-based temperature. Additionally, the skeletal plot in Figure D reveal that as the temperature decreases, the long wave radiation-based temperature tends to exceed the infrared radiation-based temperature. And we use the ground-based cloud remote sensing to identify cloud, and which is labeled with the green shadow in the figure. And we can find the cloud are prevalent during the Arctic window. Moreover, both clear sky and cloud conditions also show that air temperature is greater than the long wave radiation-based temperature, and the long wave radiation-based temperature is also greater than infrared radiation-based temperature. We also found that in Figure A and Figure B exhibit some data points about the 1.1 line compared to Figure D and Figure E, where long wave radiation-based temperature and infrared-based temperature exceed air temperature. This may result from the calculation errors caused by snow particles in near surface atmosphere, like snowfall, diamond dust, or blowing snow, which to future affect the calculation of the in-situ temperature. And this that showed the three types of in-situ temperature are used to validation models ST. Due to the misclassification of cloud condition as clear sky in the modest cloud product, ground-based cloud remote sensing was used to further filter out the misidentified pixel. Only pixel classification as clear sky by both modest and ground-based cloud remote sensing observation were included in the validation, and the results can be shown in the red point. And we can find the validation results based on air temperature show cold bears, but the results based on infrared-based temperature show a warm bears, especially in a cool environment, which can be attributed to calculation errors when near surface atmosphere exists snow particles. Hence, we use the relative humidity data, where greater than 100% is also used to remove the snow particle, and the validation results are marked the blue font. And we can find, and the results we can find the both infrared radiation-based temperature and the long wave radiation-based temperature achieve an accuracy better than 1 Kelvin in Figure D and in Figure E and Figure F. However, a systematic cloud bias is still evident in the long wave radiation-based temperature validation, which indicated that the cold bias is primarily caused by an overestimate of the long wave radiation-based temperature, rather than the uncertainty in the retrieval algorithm. We also summarize the near-surface atmospheric condition over the polar or ice surface. The near-surface atmosphere between the radiator and the snow surface typically exists 4 states, include pure atmosphere, diamond dust, snowfall, and drifted snow. However, accurate calculation of the in-situ LT is only feasible under pure atmospheric condition, when snow particles are present between the radiator and the surface, especially during diamond dusty or blowing snow events under clear sky. They can lead to thematic errors in ground-based temperature calculations. Therefore, it must be to remove the data where the snow particle exists in the near surface atmosphere. We use the radiation-based in-situ ST to validate remote ST. We think the overestimate of long-wave radiation is particularly due to the omission of the near-surface atmosphere radiation in the calculation process. Hence, under pure atmospheric condition, the motion is used to simulate the spectral transmissions of near-surface atmosphere between the radiameter and the surface, based on the humidity and the temperature data from the 3-layer meter tower in mosaic application. And the result shown by the blue curve. The near-surface atmosphere is not completely transparent, with significant observable particularly in the far-infrared region beyond 15 micron. Therefore, when the temperature invasion often exists over polygons, the contribution of near-surface atmospheric radiation to the total surface radiations increase, neglecting the near-surface atmospheric radiation may lead to the calculation errors of long-wave radiation-based temperature. And let's have a summary for the study. First, we found some particularly near-surface atmospheric significant effect ground-based radiation temperature calculations. Secondly, air temperature is always greater than the long-wave radiation-based temperature and greater than the infrared radiation-based temperature. Thirdly, under pure atmospheric condition, both long-wave radiation-based and infrared radiation-based temperature validation models are achieved within 1 Kelvin, but long-wave radiation-based validation result shows cold bias. Firstly, the bias in validation process for long-wave radiation-based temperature is attributed to uncertainty in snow surface emissivity and near-surface atmospheric radiation. Last, we recommend compare the following data for more accurate validation of the polar snow surface temperature, include the infrared radiation-based temperature like S1, SI-111, and ground-based cloud radar to remove the misidentified cloud pixel in satellite data, and in-situ relative humidity data to fit the data affected by near-surface snow particle. And last is the existing issue and future work needs to be done. Firstly, to conduct more comparative study of different temperature measurement at the same site to improve the representativeness and reliability. And secondly, to further quantify the impact of the near-surface atmospheric radiation on in-situ long-wave radiation-based temperature measurement. And thirdly, to validate other satellites and ground station use the method proposed in study to enhance its general applications. And the last is investigate whether LT is traveled by remote sensing under clear sky with blue snow or as critical represents surface snow temperature or is affected by suspected snow particles. That's all my presentation. Thanks for your attention. Thanks.
So thank you to Chenlie Shi for illustrating the importance of good validation data and the difficulties in validating ice surface temperatures. Then we would like to open the questions for these 3 first morning talks. Yes, Chris, to start, and Anita.
Thank you, Chris Merchant from Reading. And I'm wondering about another situation on the sea ice, which wasn't really mentioned when we have some sort of melting condition. So there's 2 things I have in mind. I asked Pierre about this a year ago, and when the air temperature is above the freezing temperature significantly. Of course, the radiometric temperature from the infrared could be quite close to zero, and that's quite interesting, I guess, on Greenland, for example, as an indication of melting conditions. And then also in the sea ice in the late summer, when you have melt ponds on the water, so you've got mix of ice and water surface, whether CIMR, this may be a question that will be able to tell us something about the melt pond fraction and how that's evolving over time. There's two questions there, sorry.
Yes, Jakob.
Yeah.
Try to.
Maybe I can. I don't know if I don't have the answer, but yes, it's for sure an interesting question about the melt ponds, and I just didn't include that in my talk, but we have some indications also showing that actually, well, first analysis showing that from infrared actually we see a positive ice surface temperatures in the summer, and we're wondering if that might be due to the impact of melt ponds having diurnal warmings and have a stratification in the melt ponds, if that's the case, or a retrieval issue, but that's true. And yeah, and of course the microwave signal changes completely when we have melts and where we have surface waters. So that's I'm not an expert. I'm looking at Hoyeon and Suman on that. So I'm not an expert on that. But yes, it's for sure. Yeah, it's complicated. I don't know if for anyone. Andy, if you have a comment to the question.
Well, yeah, what I was, Andy Harris, University of Maryland, what I was going to say is that obviously that's how sea ice detection works, because you get this massive change, massive factor 2 change in the emissivity. So you should be able to do something with, I mean, not necessarily, just the thermal, the retrieval channels, not the C-band, but you could go to the higher frequencies and get a very relatively good answer in terms of where the snow is wet versus not wet. So,
yeah, I agree.
So Cristina from Marine Institute in Barcelona. Yeah, I was going to say something like Andy. Indeed, I think CIMR would provide something in L-band. So melt ponds we will be somehow retrieved using the salinity retrieval. Because we have some preliminary works on the Southern Ocean, and we are able to, but it has to be like large areas of melting. But we have been able to even observe the polynyas. So this is the melting water inside in the ice. So with band L could contribute to detect that this kind of cases. Yeah.
Ida?
Hey, I have a quick question to the reference IST figure. Maybe for you, Hoyeon. I don't know if we can see it again, the one with the temperature profiles going through the snow and the ice.
Jakob's presentation.
Yeah.
If it's maybe you already said it, but the very top of the figure, before we hit the crosses and the small triangles, where is that temperature? Is that in the snow or is that above the snow?
So that's above the snow. So on the y-axis, 0 is the snow-ice interface, and X mark denotes the air-snow interface. So the thermistor string goes above the snow surface as well. So it provides the temperature from atmosphere to the water, and there's snow and ice in between somewhere.
So then it also indicates that we don't have a lot of variability from the air temperature. Okay. Thanks.
Yeah, and it's supposed to be simple, this figure. So we still have a bit of way to go, maybe.
Yeah, I mean, I think that you do have a lot of variability in the air temperature because that's the biggest error bar, if you see what I mean, the snow-air interface. So there's not maybe a big difference between the bottom temperature in the air, but it's not very much into the air. You know, it's possible to sustain a large gradient through not very much snow, but once you get to the air, you're into kind of like boundary layer process, so it's a much smoother gradient from that point on. But that's where the big variation is. But also the one thing that you haven't said with regard, sort of like, well, what about when we've got this problem that they don't quite match, and if we can do this, that, one thing you can, of course, do if you do have the snow thickness, at least if you get a good way of doing that, is you can work out what the heat flux is. Rather than having to assume the heat flux, you can actually sort of have a go at measuring it by having that infrared skin and then the temperature at the bottom of the snow, the snow ice interface. So is that on your wish list as well to extract that or try and calculate it?
Yes, I think for sure. But the problem is that we are, how to get the snow thickness, and we're using mostly the infrared and microwave difference in the IST to derive the snow thickness. Yeah, so it's a little.
The thing is, if we focus on the freezing period, for example, January to March, there's already a retrieval algorithm for snow depths and ice thickness using the infrared and microwave IST. So I can provide you more information if anybody are interested in that.
Thank you. Okay, Chris again, to last question before coffee break.
It's just a very specific question. What's happening in February at the ocean ice interface, which is not the temperature we'd expect? Simple ideas, anyway. When it's minus 2.2, why is it minus 2.2?
I don't know. Good, but I don't know, salinity issues. I don't know. It's yeah. It's. there are also some uncertainties, and these deriving the interfaces here, estimating where do we actually have the interface. That's maybe, I don't know, the uncertainty. These numbers are supposed to represent the surface temperature or the temperature at the interfaces, but they have been derived, empirically determined from the data itself. So, and if they're off by a little bit, I think they're probably you have a bias there and introduce something. Just speculation. Maybe you know more.
Some comments. I think this can be due to the rapid freezing under the ice bottom. Then as overall, this thin ice have very high salinity. Later will drop out salinity thought quite rapid, I think.
Might be. Yeah. Good point.
Okay, so that's last comment for the first part, I think, of the. Oh, sorry.
Yeah, maybe just one comment. I think this is also for the high latitude task team on the agenda to discuss this figure. So if you're interested in going into detail and discussing this, how can we make it better and understand this better? I think the high latitude task team leaders are sitting there. And
so let's put in advice for the high latitude session at 5 o'clock Thursday. We will be discussing the GHRSST conceptual figure for IST and marginalize some definitions. So that's